Меня зовут Сергей. Значит, я думаю, со многими из вас переписывались. Я скажу в основном всякую организационную информацию. Например, у нас слева здесь есть буфет, можете кушать. В 12 часов у нас будет кофе-брейк. На втором этаже зал прямо под нами. Надеюсь, разберетесь. Потом будет перерыв на обед по расписанию. Есть много-много мест, где можно покушать. Чтобы не толпиться, можно разгрестись. Ну, наверное, любим покушать. Вот. Конференция, надеюсь, всем понравится. Надеюсь, вы насладитесь ей так же, как мы наслаждались, пока ее организовывали. Потому что это было очень круто. Мы встретили замечательных людей, познакомились с многими очень классными людьми. Ну и, собственно, я думаю, вы понимаете, что, в принципе, конференция, она именно для этого. Да? То есть поговорить о C++ можем офлайн, но гораздо интереснее это делать онлайн. И, надеюсь, фана будет действительно много. Нам помогали вот несколько замечательных компаний организовывать. Но на самом деле, не знаю, в курсе вы или нет, конференция на самом деле организована сообществом C++. То есть мы проводим не только платные конференции, в течение года мы проводим встречи в разных городах, и они бесплатны. То есть мы стараемся привести разных спикеров из разных городов в другие разные города. Мы были в Новосибирске, в Нижнем Новгороде, в Саратове, в Екатеринбурге, в Санкт-Петербурге, в Москве. Ну и проводили небольшие митапы по C++. Ну, вроде бы всем нравилось. Ну, нам точно нравилось. Вот. И нас поддерживают достаточно много компаний. Вот конференцию помогали делать Касперский, Сипровер, который по студию, надеюсь, вы знаете, JetBrains. И Incredibuild нас еще поддержали. Вот. И сейчас главный спонсор у нас Касперский. Скажет пару слов приветственных. Все, спасибо, наслаждайтесь конференцией.
Спасибо, Сергей. Для лаборатории Касперского большая честь помогать в организации первой по-настоящему большой конференции C++ в Москве. Мне очень приятно, что в этом зале я вижу столько C++ программистов одновременно. Это редкость. Очень надеюсь, что сегодня и завтра мы проведем очень интересное и полезное время вместе. Спасибо.
Hello. Thank you for having me here. My apologies for not speaking Russian, and I have no idea what those two just said about me. My name is Sean Parent. I don't know how many people have seen a video of me online. Quite a few. So I gave a talk in 2013 at C++ Seasonings, which was that was the title of the talk. It was at the Going Native conference at Microsoft. And that became quite popular, and I think that's how I was discovered and invited here, although I've given many talks. I've had a very fortunate career. In 1988, I got a job at Apple, and the way I got that job was I went to a small conference like this, and I was a fairly young engineer, and I walked up to somebody who was quite well known and said, I have this idea and I know how to do half of it and I think you would know how to do the other half. Would you like to work on it with me? And he said yes. And a few months later I was working at Apple. This person was from Apple. And I think for you here, there's an important lesson there on both sides. If you're new to programming, don't be afraid to walk up and ask somebody who's senior a question, or sit down and have a chat or have a conversation. That's how you learn. And if you're a senior person, say yes. And I tried to remember that when Sergey contacted me and said, would you come to Russia? And he gave me the opportunity to reciprocate and say yes. So I'm very grateful for that. I think he's put together a great conference here, so it can never be. So he and his family have been wonderful hosts. I've been here since Tuesday as a bumbling American in Moscow who is totally lost, can't read anything, can't understand the language. His family's been great. Natalia, I don't know if she's here, from Yandex, gave me a wonderful tour of their facility. They were great. Zoltan gave me a wonderful tour of Moscow yesterday, so thanks for that. You guys have been wonderful hosts. After working at Apple in 1993, 1993, I took a job at Adobe. Anybody who knew who Adobe was at that time thought PostScript. And I joined a small team called the Photoshop team that nobody had ever heard of. And this was before digital cameras. And when my family asked me, "What are you doing?" I said, "Well, I'm working on photography on the computer." And like, what does that even mean? Right? But it's been a wonderful product and a wonderful experience. I kind of like this slide. This is disconnecting. Adobe has a great art department, and they just keep throwing out stuff. So I thought for concurrency, this is a great slide, especially since eventually during this talk, the time is going to be correct. So at Adobe, I've been there almost 20 years now. I worked at Google in the middle for about a year. And lately, I've been working on software for mobile devices and digital imaging software. And this talk is going to be about concurrency. At the Going Native conference, I gave this talk, C++ seasoning, and I gave 3 goals for better code. And a lot of people after that talk asked me to write a book. And I said, okay, well, here's what I will do. When I'm invited to give a talk, I will try to flesh out a section of the book, and I'm also teaching a course inside Adobe on programming, and so I'm working on the book for that. And so this is kind of where I am. This is the outline of the book. And here we are at concurrency. And our goal is going to be no raw synchronization primitives. There are some common themes that are appearing as I'm putting this together. One is that building software at scale, is all about managing the complexity of relationships. How do all the components interconnect, and what does that mean? I believe it's very important to understand the fundamentals, and I mean that to a very low level. The first chapter in this book, I start with how do transistors work? How many people in this room know how a transistor works? Few. Yeah, better than in the US whenever I've asked this question. I get nothing. I think it's very important that you understand the machine that you're working on. And then I think it's very important to learn how to code simply. I think as software engineers, we tend to create very complex solutions to very simple problems because we don't understand them. If your solution is complex, it probably means you don't understand it yet. So keep working on it. I want to give 2 short demos. I've got to unplug here. Okay. This is a product I worked on about 4 or 5 years ago now. It's a product called Revel from Adobe. Not many people have heard of it. It hasn't been a huge success. I still think it's a good product, but we've been taking the ideas from Lightroom. But there's 2 things I wanted to show you about it. One is this is a very large collection of images, and you'll see as we pan, they're filling in asynchronously, and that's actually fetching them all over the internet as we go. Right, and so you can scroll through this and scroll back. And the other thing I wanted to show, this is one of the images in my collection. This is actually the daughter of Tom Hogarty, who's product manager on Lightroom. This image is a 37 megapixel image off of a Leica S2 camera. And we can zoom way in. I don't know if you can see. You can see the hair. It's actually higher resolution over here, but you can see the hair, the texture of the fabric, all of the detail in this image, the tear in her eye. And we can edit this right, in real time. We can do that, right? So it's all very smooth and very fluid. Now, when I was working on this at the time, it was for an iPad 1, and we had pretty much the same experience for this size image. This is an iPad mini Retina, so it's quite a bit more horsepower. But the device is still too slow to actually do this, right? What I'm showing you is smoke and mirrors. Our rendering engine is a non-destructive engine, so you can come back in and make adjustments, and we can go back and get our original image back. And so we're processing this very long imaging pipeline. It's a 40-stage image processing pipeline, live for every pixel as you see it. And it's not fast enough to give 60 frames per second on this device of an appearance. So what we actually do is we pull off an illusion where we will render the image incrementally. We will render it at a low resolution first and then fill it in. When you do a pan, an animated pan, we have two layers, one low resolution so you don't see black as you pan, and then we start rendering where that animation is going to stop. So that gives us a quarter second to do that render while the image is sliding across. So the appearance to an end user is that it's all very fluid and very live and very high resolution. And if you actually kind of slow it down a little bit and look at it, it's not. So this is one reason why of late I've been very interested in concurrency and how do you provide this fluid experience in a product so that the user doesn't have to wait, which means we light up the machine. So you guys get to see something here that hasn't been shown publicly before. This is a first. I had to give permission to give this demo. So this is another 37 megapixel Leica S2 image. It's a RAW file. So if you look, that's a 36 megabyte file on disk. This is a Chrome browser with no plugins installed. And we're going to drag that image into Chrome. And there's the image opened up. And this is the same rendering system that you were just looking at. It's the same rendering system that's on Lightroom Desktop. And this is running entirely in the browser. Right? So you can see it's a RAW file. You still have all the details there. It's not quite as bright on the display. Let me brighten it some more. Okay. Now in this case, the way we're doing that is we compile several million lines of C++ code using Google's Pinnacle technology. How many people are aware of Pinnacle? Right. That stands for Portable Native Client. This is something that Google is promoting for Chrome. So you basically compile into what's roughly LLVM bytecodes, and then that gets delivered over the web, and Chrome has the back end for the compiler, and it finishes the compiler inside the browser. So in this case, the performance isn't so great. Isn't so impressive because it's, at the end of the day, it's pretty close to native code. We're missing a few things. We don't have SIMD support in here, but we do have threading support. So on my machine, this is lighting up all 8 cores on the desktop. But this is exactly the same code. Pick up this image. This is off a raw file from a Sony RX1. And this takes a moment to open. So we're aware of this issue. We're working on the performance for this part. But the issue here is Safari. Safari does not support Google's portable native client. I have no plugins installed in Safari. So what I did is I took the same code base and compiled it with the Emscripten compiler. How many people are aware of that? Small number of people. So this is a compiler that Mozilla's been working on that compiles C++ code into JavaScript. Okay? So this is executing the desktop Lightroom rendering engine inside of JavaScript, and we still get good performance here. So we still get good performance here. We can slide the sliders around, adjust the image. We can do horrible things here, crank the vibrance. Okay. So we can still edit this image in real time, even though this is a raw file from JavaScript inside the browser. And we can do fun effects like that inside the browser. Now, our biggest challenge here is that JavaScript has no threading support, and Emscripten doesn't help you there. And so this is all running the same code base, but it's single-threaded. So we're trying to get performance that appears to be on parity between running native on 8 cores and running through JavaScript on 1 core. Okay? And so our code base has to be able to scale, right? We have to utilize concurrency and parallelism when it's available, but be able to scale all the way back and run single process. Right? And still be able to do things interactively. So the reason for this little button with the wiggle is that while that's wiggling, I can be adjusting the exposure, okay? And I can be doing those things simultaneously, right? So we still have concurrency, even though we have no thread support. So, it's important to understand the difference between concurrency and parallelism. Concurrency is when tasks start and run and complete in overlapping time periods, but don't necessarily execute simultaneously. Right? Parallelism is when things execute simultaneously. So if I have a tasking system where I keep feeding tasks to a queue and they get pulled out of the queue and executed, that gives me concurrency. Okay? But if I can actually kick up threads and execute 2 threads simultaneously, that gives me parallelism. Okay? So concurrency is a requirement for parallelism, but not the other way around. Now, one of my strong goals when I deal with product teams is no raw synchronization primitives, right? And what do I mean by that? What I mean in just some arbitrary piece of code, I don't want to see synchronization primitives like mutexes, atomic, semaphores, memory fences, condition variables. Okay? What I want to see developers do is, if they have a need for those things, figure out what is that mechanism and package it up into a mechanism. Okay? So that they use some reusable component that they can use in multiple places in the code. Right? These are way too low level. If you're just sprinkling mutexes in your code, I will almost guarantee you your code is wrong. Okay? Now, why do we care so much about this stuff? Right? At Adobe, we do a lot of imaging, right? We do video, we have Photoshop, we have Lightroom. And my goal, and I think many of the team's goal, is always to take your machine and run it so hot that it melts through your table, right? Right. We want to light that entire machine up. If we're not, a competitor will, and they'll start touting that their operations are faster than our operations. Over time, that's getting increasingly difficult, and I don't think many people have a good idea of how a modern machine works, or of how a modern machine looks on a desktop. So this is kind of a breakdown of where the performance is on a modern desktop machine. If you look, more than 2/3, almost 3/4 of the performance is wrapped up in your GPU. Okay, about half of, or 2/3 of what's left, you can only get to through vectorization, which is using the SIMD instructions, which these days is typically fairly hard. There are a couple compilers, like the Intel compiler, that will try to do some level of auto vectorization. Most of the time, you're still doing it by hand. Okay, there are also some tools like OpenCL, which you can compile to not run on your GPU, but to run on your CPU. Varying degrees of success there. Okay. Then you get into multi-core, and how do you support multiple cores? If you're not doing that, that's the amount of performance you're giving up. And finally, if you're just writing straight single-threaded C++, you're down to like 0.025% of the machine that you're utilizing. Okay? So if you're just lighting up one core, no SIMD instructions, no GPU support, you are wasting more than 99% of the desktop machine. Okay? I don't think many people get that. So let's talk a little bit about the difference between threads and tasks. Right? A thread is an execution environment consisting of a stack, a processor state, running in parallel to other threads. And threads are relatively expensive. Modern OSs have reduced the task switching time down to something that's relatively tight and reasonable. You still have a relatively big memory footprint because you have to allocate that stack. You have some amount of shared memory that you're allocating in your kernel. So most operating systems will put a cap because that kernel memory has to be wired down, so eventually you run out of threads. Where a task is a unit of work, some function that you want to execute, and that could be executed on a thread, or it could be executed mainline, which is just another thread. And the usual thing that people do is they schedule tasks to a thread pool to optimize the machine utilization, right? If I've got an 8-core machine and I light up 100 threads, okay, I'm not getting that much parallelism. All I'm doing is I'm forcing the kernel to keep interrupting one processor, switch in to another thread, execute some on that, switch to another thread, blowing my caches. Okay? So I don't want that. What I want to do is I want to keep the code together, executing on one processor. And so the usual way to do that is to schedule tasks in a thread pool. Right? C++ 14 doesn't yet have a tasking system. I'm hopeful that C++ 17 will. I know there's been lots of discussion about it. But C++ 14 does give us some primitive thread support. And it does give us something called futures. We'll talk more about futures in a bit. Now, getting performance out of a system is really hard. How many people here have heard of Amdahl's law? Yeah. So Amdahl's law is pretty simple. What it states is that if you have some amount of your code in your product that has to execute serialized in sequence, okay, then that's going to limit the total performance of your system. Okay? So if you search on Amdahl's law on Wikipedia, this is the graph you'll get. This is the equation for Amdahl's law. And everybody puts this in your slides. And I hate this picture of Amdahl's law. The reason why I hate this picture of Amdahl's law is it's logarithmic in scale across the bottom. Okay, so if you look down there at number of cores, it goes 1, 2, 4, 8, up to 65,000 cores. But it's linear on this axis. Okay, so I've got 65,000 cores, and what I'm showing is I'm capped out at 20x performance increase if I have 95% of my code running parallel. Okay, if I put a line on this graph that was linear, that was what if there was no cost, starting down here and going up, right? That line would arc up because it's a logarithmic scale. And the top right corner of that line would be about halfway to the moon. Okay? So this really doesn't give you the impression of how bad Amdahl's law is. Right? So this is my graph for Amdahl's law. So it's the same equation, but now we're on a linear scale, and we're just looking at it near the origin, which if you work on desktop or even server-side Linux machines, that's most of where you care about. Okay, very few people have a cluster where they've got 65,000 processors that they're fanning out tasks to. Okay, so what we've got across the bottom is a scale that just takes us up to 16 processors, which is probably farther than most people go. And then the red line is linear performance. And each line going down from that represents 10% serialization in your application. Okay? So if you have a mutex in there, which is blocking execution of your code, you get to tick off some small percentage point. Okay? And that takes your curve and just bends it down. Okay? Getting to a shared resource, like memory is a shared resource, bends you down. Okay? You want to stay in your caches. So, using a condition variable also requires a lock, bend it down. Okay? So if you're sprinkling these things all over your code, you're really quickly going to find yourself down in the yellow area, right? And I've seen a lot of programmers who are new to threading who end up at the point where when they hit 2 cores, it actually runs slower because of the overhead for the threading, right? I went in a presentation just the other week on a system where the scaling looked like at 1 core, we'll call that 1.0. At 2 cores, we were about 0.7 performance. At 3 cores, we got back to about 0.9. And at 4 cores, it got to about 1.2, and then it was flat. Okay? So these things happen. This is, in general, what makes a concurrent system slow. You can read it down, slow, right? Starvation is when you're not able to keep feeding the beast, right? You have to keep feeding tasks to the machine. Latency can be stuck waiting for something coming off the disk, coming over the wire, coming in from memory into your cache. Overhead is how much it takes just to communicate between the threads, between your tasks, put things together. And then the killer down there is waiting. How long are you just stuck spinning? Most developers that I talk with have this view of multi-threaded programming. They think, well, what I will do is I'm going to have my object, and I'm going to share my object between a bunch of threads. So the way I'm going to do that is I'm going to stick a mutex on it, okay? And each thread will just acquire a lock on the mutex, and that will control the access. Okay? This does not scale. Don't stop. Don't put weights in. So most platforms, if you're working on them, have some kind of tasking system. Okay? If you're on Windows, you've got Windows Thread Pool, and you've got what does PL stand for? Anybody? Yes, thank you. Apple's got their Grand Central Dispatch, which is also known as libdispatch. Libdispatch is open source, so you can bring that up. It's a nice system if you want to bring it up on Linux, and we also run it on Android. Intel TBB has a very nice task system. That's thread building blocks. That's also an open source library supported on many platforms. HPX is out of the Stellar group at, I'm drawing a blank on the university. Hartmut Kaiser is the person who works on HPX. It's another open source project that's targeted how do you do grid systems and very large scale concurrency. Okay, so these things you probably have available. Okay. Now, in my case, I found myself bringing up a system inside of a browser, and I didn't have a tasking system. So I needed to write my own. So the first thing I did is I looked online, and there's a credit, it's too small to read in the bottom right corner. This design comes off the Oracle website. They have a very nice book, online book, that you can read on programming multiprocessor systems. Okay? And they come along and say you need a task system, so here's what you're going to do. You've got a bunch of threads that are running at the bottom, and you need to build a queue, and you're going to feed data into the queue, and then you're going to pop it out the bottom. And that's their design. Okay, so this is pretty easy to write. So I'm like, okay, well, let's write it. They have a lot of code, but I don't like to write a lot of code. So this is my code. It's pretty short. So I just declared a lock type. This is going to be a primitive that I'm going to construct, which I call a notification queue. So the idea with just a notification queue is that you can wait on a notification queue, and when something comes into it, it wakes up whatever's waiting on it. So it notifies whatever's waiting on it. Okay? And I'm just going to use an std deck as my queue. It's going to hold a deck of functions, right, which are going to be my tasks. I'm going to need a mutex, bad luck, and a condition variable to pick things up. Here's what my pop function looks like. Okay, I'm just going to lock my mutex, and then I'm going to check and see if my queue is empty. If it is, I'm just going to wait. So otherwise, I will grab the front of my queue off. So that's 2 lines to grab the front, right? We're going to move it out and then pop it. My push, similarly very simple. I'm just going to acquire my lock and then in place back whatever I'm pushing into my queue. And then I'm going to notify everybody who's waiting on the condition variable that it's ready. Okay? How many people here have used condition variables and mutexes? Good. Okay. So now I'm going to take my notification queue and I'm going to turn it into a little task system here. So we'll get a count for how many processors we have, which C++ 11 and 14 both provide that as our thread hardware concurrency function. We're going to create a vector of threads, okay? And then our notification queue. Right? Now this is what's called our dispatcher. Okay, this is our run function that's going to be running on each thread. Okay, so all we're going to do is we're just going to keep looping forever on that thread, and we're going to pop our function out of our queue, okay, and then we're going to execute it. So that's popping our task out of our notification queue and executing it. That pop will just wait, right, if there's nothing in the queue. Okay. We'll initialize our task system by just taking and pushing a bunch of threads that are attached to this run loop. Okay. The unused variable I there, we'll end up using it in a bit. That's there just to tell us which the index for this thread within the queue. To destruct it, well, for now we'll join all the threads, but we're never going to get there because we're stuck in the infinite loop. We'll fix that. And then we need a way to put things into this task system. So this is going to be our async call. So we hand our async call a task, which is just a function, any kind of function object that takes no arguments, returns void. Okay, we can pass it in there, and it will push it onto our queue. That will notify a thread that's waiting. That thread will pop it out of the queue, execute it. Everything's happy. Okay. Let's go fix things up here. I don't like the fact that we're just hanging on quit because we can't join our threads. So we're going to add a flag that says that we're done. We'll add a function that lets us set our done flag and then notify everybody who's waiting that we're done. And then we'll just change our pop so that we're checking on our done flag here to see if we're done. Okay. Now we have to be a little careful that we could be done but not empty. Okay. So what we want to do is say if we're not empty, we return false. If we're empty, we return false. Not if we're done, we return false, because we want to make sure we clear out the queue before our little app quits. Okay, so that's our design. How do the people think it performs? There's our speedometer there. Does this work great? No. Why not?
Because of logs.
Because of logs, right? We have a huge amount of contention here. Okay, nah. It's not good. Okay, I don't know how many servers are running Oracle's code. It kind of scares me. Okay, so we're doing exactly what we said not to do, right? Right? We've got our tasking system, which is an object, and we've got a whole bunch of threads banging on it. Okay, and we're switching the mutex around. So that's exactly what we said up front, that we're not going to do that. Right? We're trying to fix that problem. And it sucks. Okay, so how do we fix it? Well, here's the typical way to fix it. Okay? We're going to take a scheduler, and instead of just having one queue, we're going to have a bunch of queues. Okay? We're going to have one queue per thread. And when a task comes in the top, we're going to feed it to one of those queues. Okay? And then at the bottom, we're going to have our threads waiting on their own queue and sucking it out. Okay, so this is going to release or reduce our lock contention. So we could build this. Okay, so this is our task system. Now we're just going to take, instead of having one notification queue, we're going to have a vector of notification queues. Okay. We're going to use an atomic here for our scheduler to tell us where we are. Or which queue to put our item into. Okay, and so now here's what we're going to do, is we're going to take and put it into, well, this is our dispatcher, so we're going to take and pop out of our own queue. That's where that I was needed. Okay. Then down here, when we clean up, we have to clean up multiple queues, not just one, so we notify them all that we're done. And then when we push here, here's where we need the atomic increment on our index, okay, and then we're going to push it in for one queue. Okay, what do people think?
Bad.
Bad? Better?
Not better.
What, not better? It's better. It's better. It's about there. Okay, it's not great. Why not?
Tasks take different time.
They take different time. Tasks take different time. Yeah. So when tasks take a different amount of time, right, we might feed in a long-running task into one queue, and we're just rotating around. So we'll keep sticking more stuff on top of that task in the queue. Okay. And eventually, what's going to happen is we'll get to a point where we're starving. We have one thread executing this long queue, and everybody else is just sitting idle. Okay. Okay. So that's one problem with it. What's another problem with it? So we still have a fair amount of lock contention going on here, right? Right. If I'm putting tasks into this regularly, right, I still have I'm going to be acquiring a lock, putting it in there, doing the notify, and I can very quickly come right back around the system.
Thread could occur in its own queue. If some thread needs to queue a task, it can put it in its own queue. So it doesn't need a lot of.
I'm not sure I followed that. Yeah. Okay. Okay. So we're doing that. So let's see if we can fix this. What we need is a task scheduler. Okay? Or I'm sorry, a task stealing dispatcher. How many people have heard the word task stealing? Right? Right. And how many people think it's something fairly complicated? A few people. Yeah. How many people have ever tried to implement one? A couple people. Good. Yeah, a lot of times if you go and you like research it, you'll get very complicated descriptions of how task stealing should work. But the idea is fairly simple, which is if your queue is busy or empty, okay, pull something from somebody else's queue. So how are we going to do this? Okay. We're going to add this function, which is a try pop. It's very similar to our pop function, okay, except now we're not going to wait. Okay. We're just going to try it real quick, and we'll return a bool if we got it. Okay. If we didn't get it because we couldn't get the lock, because that lock was under contention, then we'll just return false. Okay? And in this case, we'll just treat it as if it were an empty queue. Okay? A busy queue is equivalent to an empty queue, as far as we're concerned. Okay? We're going to also add a try push, right? We don't want the lock contention at the top either. Okay? So we'll try to push something in, and for our scheduler, if the lock is busy, we'll just return false and say, yeah, we couldn't put it in. Okay? So now in our task system, inside of our run loop here, okay, all we have to do is spin around each queue trying to pop. Okay? And what I did is I said, just run one time through all the threads, and then if you didn't get anything, then park and wait. Okay? So you can run once around the loop, and if you didn't hit anything, park and wait. Now, if you're running on a machine that has very little concurrency, maybe 2 cores like this, you might want to run around a couple times, right? You could actually put a timer on that. Say, we'll spin for a moment and wait. Okay? Similarly, when we put things in, I'm going to run once around, okay? And if we can't put it in, then we'll do a wait push. Okay? Now, on the push, you're guaranteed that eventually somebody's going to be free, right? So you could actually just make that a spin loop, right? And just spin around until you find a free one. Okay, what do people think? How do we do, performance-wise? Better, yeah. It's pretty good. Get over there. The top mark on my thing is what I get benchmarking Apple's GCD. Okay. Now, Apple's GCD is a very complex implementation. You can look at it, it's open source. I couldn't just, even though it's open source, I couldn't just bring it up inside the browser because it has dependencies on things like libkern, and inside the browser I don't have a kernel. And if I actually play with this and tune it, I can match their performance in most cases. There are some trade-offs there, right? I'll spend a little more time spinning, I'll speed up some things and slow down other things. So overall, I'll give me a 9 and them a 10. They're also doing things like scheduling tasks across the entire machine, not just one process. Right? So they have a few advantages and insights that I can't get to. But this system does pretty well. And the nice thing about this is you can build this very simply, and you can play with it, okay? And you can use this to experiment with the tasking system. And I encourage engineers to do this. If you look at my development machine, I have one main.cpp file inside of my IDE that at this point, I don't know, is a bazillion miles long. And every time I write something, I just conditionalize out the last thing I wrote, and I write it in there. Okay? And it's just a little scratch project. And even if I'm working on a big product, I try to get whatever component it is I'm working on, working there with no dependencies first. Okay? Okay? And then drop it into the product. And that way you know your system's very modularized. If people want to come along and take it later, it's very clean, comes right out. Okay? So I try to write all my code in that environment. And this gives you a nice way to play with the tasking system. So that just repeats what I said. How many people here have used futures? Quite a few. Last conference I asked this, it was like one hand. How many people here at least know what a future is? Same number of people who use them. Okay. Okay. So I'm going to give a little bit of a simplified view here of futures. But the idea with the future is when I have some asynchronous task, if I have an asynchronous task that takes no arguments and returns void, okay, Bartok would kill me because that's not a very functional design. Right? It's just can't do anything. And in truth, it really can't do anything unless you have some additional mechanism to get information out of that task. Right? And how do you synchronize communicating information out of that task into something else? Right? So even the ones developers come along and they say, okay, I understand, I want a thread pool, I'll create my thread pool, I need task stealing, maybe I'll use the system thread pool, I'll create these tasks that have no arguments, return no value, I will drop them in, and then I'll sprinkle a whole bunch of mutexes around my code to get information back out. Okay? Stop it. Don't do that. So, what do we want to do here? What we want to do is take a function that returns some result. Okay, so I'm going to take Fibonacci. Fibonacci is something that everybody uses when they're demoing threaded code. Okay, the CPP int type there, everybody knows boost somewhat. So CPP int is a multi-precision integer. Okay, so I'm going to take Fibonacci of 1,000,000. Okay. Anybody know how big that is? It's pretty big. Okay, so I'm going to take Fibonacci of 1,000,000. I'm going to calculate that asynchronously, and I'm going to get a future for it. Okay? A future is a token for the result, right? Right? It's like an IOU. Okay? Okay? At some point in the future, I can take that future and extract the result from it. So then I'm going to do something complicated, and then if I were in C++11, I would call x.get, which is about the only way I can get information out of my future, and it will wait until that thing executes and then hand me back my value. So I better have a whole bunch to do in there with the do something. Okay. How many people have seen Fibonacci used as an example for the code? A bunch of people. This is my public service announcement because this drives me insane. Okay? I'm not using Fibonacci the way other people use Fibonacci. What everybody else uses Fibonacci for is showing how you do parallelism and how you can calculate Fibonacci in parallel on a whole bunch of cores. Okay? And the typical demo is, look, with 8 cores, we can calculate a Fibonacci of 27, right, in 3 seconds. Right? It's ridiculous. Okay? And the reason why it's ridiculous is because everybody uses a recursive algorithm for calculating Fibonacci. How many people have seen a recursive algorithm for calculating Fibonacci? Right? Right? How many people know that there's a better way to calculate Fibonacci? A couple of people. Right. So for those of you who don't know, we're going to learn real quick how to calculate Fibonacci. Okay? So this is a total aside, has nothing else to do with the talk. It's just my public service announcement. Okay? So this is a power function. What do I mean by power? It takes some value, t, okay, rate of type t, raises it to a power, which is some integer number of type n, okay? And what do I mean by power? Well, some operation. So if I plug in addition as my operation here, and then my power function does multiplication, okay? And if I plug in multiplication, then this is just a regular way to think of raising the number to that power. Okay, so I can plug in my operation and make this do quite a bit. Okay, the algorithm here, I'm not going to walk through it, but it's known as Egyptian multiplication. It's also known as the Russian peasant algorithm. No offense intended.
If you want a lot of detail about this, you can see Alex Stepanov's book.
From Mathematics to Generic Programming. It's a wonderful book, highly recommended. Okay, so that's a power function. Okay. So now we want to calculate Fibonacci, right? So Fibonacci is a linear recurrence. And so that means that if you're typically doing the recursive form of calculating Fibonacci, you're doing a ton of work that's redundant. You're calculating the same values over and over and over and over and over again. Okay? So the way you want to calculate Fibonacci is you take a 2 by 2 matrix, which is 1, 1, 1, 0, it's known as a Fibonacci matrix, and you raise that to the power that you want for the Fibonacci number, right? Our power function there is a log n function, okay? And so here we just we have a little function to multiply a 2 by 2 matrix. We create our Fibonacci matrix there, okay? And we raise it to, it's actually n minus 1 power, okay? And then we just extract the top left corner of the matrix, item 0, and that's our Fibonacci number. Okay? If you want details about all the math and all the history of it, read Stepanov's book. Okay, so this is the result. Okay. That took less than a second to calculate. Okay. It took way longer to scroll by. It's 208,000 digits, almost 209,000 digits. Okay. And so it just really drives me nuts when I see people calculating very small Fibonacci numbers very slowly as a way to demonstrate how you do parallelism. And I see things, no offense to Zoltan here, who knows Charles Simone, who did intentional programming. One of the early examples of intentional programming was, oh, here's how you would derive this really bad recursive algorithm for calculating Fibonacci. It's like, don't use it as an example. Okay? So this is just running on one core, and any of the parallel things on a grid, I can smoke them. It's logging calculation. So let's get back. Enough about Fibonacci. We do this. So here's conceptually what we're doing, right, with our future. We're taking our function and we're separating it from the result, right? So we get a token of the result and we can pass the results around, and somehow, magically, the information when that function executes has to feed over to the result. Okay? So what futures are is they allow us with a fairly minimal code transformation to start to express the dependencies, right, between elements in our code. Right? I got these arguments attached to this function, my result is dependent upon that. Okay. Now C++ futures have some features, like they will do exception marshalling, so if your function throws an exception, that will propagate back to your future. They do what's called sever notification, which means that if the sending side, known as a promise, right, the other half of the future of the promise, if the promise destructs, then the future will receive an exception that the promise was broken, right? So if they wait for the result, instead of waiting forever, an exception will get thrown and say, nothing's ever coming here, right? The sender went away. C++ 14 futures lack a whole bunch of features. I'm hoping some of these will get into C++ 17. There's a bunch that I don't think will. One thing that we need is we need a way to do continuations, right? If this thing is a token for a value, I don't want to wait on it. What I want to do is establish the next dependency. When this value is ready, then do this other thing. Okay, so that's called a continuation, and partially coming out of work at Microsoft, they end up getting called .then clauses. Okay. Then we want a way to do joins. Okay, a join is when I want to say, okay, when these two futures are ready, do this next thing. And that doesn't mean wait on those two futures, right? What you want to do is basically create a little a function object that has a count in it, and every time one of the futures is ready, its continuation clause decrements that count, and when the count hits 0, then it fires the next thing in the chain. So there's no waiting on a win all. Okay. For me, it's very important that I have a cancellation facility. When I gave you the demo there, where I'm scrolling through a whole bunch of images, I might be requesting an image and get a future back for that image that I'm going to display, and then before that future is resolved, the image scrolls off the top. Okay? I don't want to be chewing up network bandwidth. I don't want to be rendering that image anymore. What I want to be able to do is say, if my future destructs, then the operation becomes a no-op. Okay? It doesn't execute. Okay? I do not think that feature is going to be in C++ 17 futures, unfortunately. The other thing that's important is progress monitoring. If I have a task that spans out and does a bunch of subtasks, I would like to be able to let the user know where we are in the process of resolving all this. Right? How long is it going to take until we complete? The only progress monitoring that we have with current C++ futures is to notify you of whether or not a value is ready yet. So you can at least check it and say, are you ready or not? And that has a couple issues that I'll discuss in a moment. Okay? And C++ 14 futures don't compose easily to add these features. So even though they're lacking them, it's very difficult to figure out, at least I haven't been good at it, to figure out how would you then layer them, how would you layer these features on top of C++ futures. So let's talk about what we're doing with continuations here. Okay, so we've got our functions that returns a value, and then what we want to do is say when that's ready, we've got another function, return the value. Okay? We don't want to be blocking on get. Okay? In fact, in the tasking systems that I build, I don't have a get. Okay? Well, I do, but it's for debugging purposes only. Okay? So the problem with get is you're just stalling one of the threads in your task pool, okay? And you have to have a fairly sophisticated task pool to recognize that one of those threads is blocked, and it can spin up another thread and try to balance things out, okay? And any dependent tasks on that thing are stalled and aren't getting executed. Now, most other tasking systems have some form of continuation. Take a lot of different complicated forms. Okay. So here's what I'd like to be able to write. I want to be able to take our Fibonacci number for 1,000,000, and then I want to say dot then print this thing, and then we would just wait for it to print. Okay. Slide out order possible. That is a win all. Okay, so for a win all, here's what I want to be able to do. I execute two asynchronous functions. Maybe I calculate Fibonacci of 1,000,000 and Fibonacci of 2,000,000. And then I want to say when all of those are ready, okay, and this is using boost continuations here for the then clauses, which is probably close to what we'll end up with in C++ 17. So what I want to say is when all x and y, then multiply the two Fibonacci's together. Right? This kind of drives me nuts. This is a pretty complicated statement, and it's complicated for a couple of reasons. The moves are there because futures are not copyable types. They're not fully regular in boost. Okay, they're move-only types. I can have a shared future which is copyable. Okay? So I could replace these with shared futures and then do the copy. Now, my win all feature here, when I call win all, what's passed to that lambda expression, to my continuation there, right? I say win all, then a lambda function there. What's getting passed in is a future to a tuple of futures. Okay? So this is why I have this horribly complicated thing here. right? What I need to do then is first I have to get the tuple out of my future to a tuple, and then I have to get each of the values out, and then I can do the multiplication and then return the result. I don't like this interface. I want to just get passed in here the value. There's no need for me to be calling get. The future should be ready, but one reason why they do that is because they're trying to support things that have non-regular semantics, and that gets very complicated. So they want get to only be callable once, and it returns the result as an R value, and that just makes life very complicated. So there we go. The result for this, if you're curious, is 627,000 digits, and Apple's Keynote broke when I tried to put it in scroll by, so I won't show it. Okay, now here's the other primitive that I want. If I can put two things together, okay, I want to be able to split. I want to be able to say, I've got this token for a value, right? I want to be able to pass that value to this function and to that function. Okay? Would seem like a nice general thing to do. Okay? You would think that you could just write this. Okay? I get back a future from calling async on my Fibonacci. Okay? And then I want to calculate, what am I doing? My Fibonacci times 2. But I also want a future for my Fibonacci divided by 15. Okay? I want to do that. I want to calculate two things based off that one value. Here's what I get with boost. Okay. The reason is boost doesn't let you attach more than one continuation to a future. Okay? You cannot do it. So I can't create that dependency graph. So my desired behavior. A future should behave as a regular type. It should behave as a token for the actual value. I should be able to pass it around. Okay, I should be able to add additional continuations to it. I should be able to attach multiple continuations to it. Shared futures let me pass futures around, but they still don't get around the fact that I can't do multiple continuations, and I also can't do multiple gets. So if I have a shared future and I pass it to two functions, if they both call get on it, the first one will succeed and the second one will crash. Okay? It's really not nice. Okay? Releasing the last instance of a future should cancel the operation. With the C++ 11 design, what I have right now is I can detect a broken promise, okay, but I can't detect an unneeded value. Okay? So if I just gave up all of my futures, it will just go and calculate it anyways. Okay. So how would we build such a thing? Right? Let's do this. Okay. What we're going to need is we're going to need some sort of shared state between our function and our future. Okay? And if we want to have multiple continuations, then we want to transform the shape into something like this. Now the dotted lines here represent weak pointers, okay, that don't hold on to the resources. And the solid lines represent our regular shared pointers, so strong pointers. Okay? So my futures, I have two futures at the end there, are hanging on to strong pointers. Okay? So as long as those two are good, everything in the system is intact. But if I drop one of those, then anything along the line will unravel. So if I drop the shared future in the top left, then it will drop this bottom guy, and it's going to no-op the function that's referring to it. So if my image scrolls off the top of the screen, I can stop fetching it. Okay. I had to do a little bit of metacode to pull this off. If you have Boost, there's a function traits library that would give you a result trait. Unfortunately, result of doesn't do this. But basically what I want to be able to do is say result of and give it a function signature and have it tell me what the result is of that function signature, right? So this is just a little meta function to let me do that. Okay. So we're going to have a class that's a package task. A package task is what we call the wrapped up function side of our future system here. Okay, we're going to take our task, end up with a package task that has a void result and a future for the result of the function. Okay. So here we'll define what our package task looks like, and we want it to hold a weak pointer to our shared data. Right? The functions don't hold on to anything, it's just the futures that hold on to data. So here's what my future looks like. That's got a shared pointer, so that's going to be a strong link. And we're going to need a continuation clause or a then clause, which will do something. And so we can make this output data. I'm going to go ahead and we'll provide a get. Okay. Our package task here, I already mentioned we got the weak pointer, and then it's going to have a call operator on it, so we can call our package task as if it were a function. Now C++11 package tasks, even though they have a call operator on them, it's non-const and they're not copyable types. So I can't put a C++11 package type into an std function, and that's very inconvenient. Okay. So in C++11, the way the interface works is you create your package task, and then from the package task, you extract the future. There's a call on the package task class that says get future. Okay. That API is wrong because I don't want my package task to actually have ownership of anything without the future. So if I created a package task here, I would have to provide some extra mechanism to like stay alive until somebody gets a future. Okay? And that could potentially cause a number of issues. So instead what I'm going to do is I'm going to provide a separate function, okay, called package, where I will hand it a function, okay, and it will return a pair of my package task, my function with the result sliced off, and a future to the result. Okay. So I'll make them both together. And I will make that function be a friend of both my future and my package task. That's the only way I'm going to create these guys. Right? So I've got a explicit constructor for both my future, it's private, and a constructor for my package task. One is taking a shared pointer, one is taking a weak pointer. Okay. And this is the implementation for that package function, right? So we're going to make some shared state somewhere. And then we're going to make a pair of a package task, passing it that pointer, and our future. Right? So that's all we need to do. So now all we have to do is define what the shared state is. Okay. So here's the idea. We take a package task, and we call it like this. We say we want to package a function that has the signature int double. We hand it some function that's callable like that. I can't just deduce it from f, because f could be polymorphic, right? It could have auto parameters. So you have to provide the signature, just like std function. And then I'm going to get back a package task that's callable as if it were a void taking a double, and my future for the int. So I'm doing that split. Okay, so here's how I'm going to create my shared object. Now, you have a little bit of a problem here in that you want your future if I've got a future for an int, it only knows about int. It doesn't know about the function that's returning the int. Okay? Because I want that to be interchangeable, right? I can have any function generating a future to an int and pass it to anything taking a future to an int. It is the package task side that knows about the function that's stored inside of it. So the way I'm going to do that is I'm going to split my class into two halves here. And I'll use inheritance as a mechanism to do that, but this is not public inheritance in any ways. This is just a mechanism inside of our futures. So I create a vector of our type. It's not because I want many types, it's because I want 0 or 1 types. And in C++ 11, we don't yet have optional. So this is a poor man's optional. I just create a vector. Okay. I'm going to need a mutex in here. I'm going to need a condition variable to notify anybody who's waiting on a get. I need a vector of my continuations. My continuations are all going to be functions taking voids, and we'll see how that gets wrapped up in a minute. Because it's my base class, I need a virtual destructor. Okay. And then I'm going to define my shared type. So the way I'm going to do that, I'm using the same trick that I've used a few times in this talk, where I first declare it taking a single argument, but I never define that. And then I declare the signature as a specialization, taking the result type in some number of args, and that lets me extract that result type in the args out of what's passed to it. Okay? So this is going to hold the function that we passed into it. Okay? And so it can be constructed to hold that function. Okay. We walk through that. Okay. So our package task is going to be a weak pointer to one of these shared things. Okay. And that's our constructor for it. We just updated that to actually have the type signature. Okay. And then this is going to be the implementation of our call operator. Okay. What we're going to do is we're just going to call some call. We're just going to forward it. Right? We're going to call some call operator on our shared data type. But first we have to do the lock. Right? Everybody used a weak pointer before? Most people. Okay. So the idea with a weak pointer is that it's a thread-safe mechanism. If you can convert a weak pointer to a strong pointer, right, by calling lock on it. And lock will either return a shared pointer to that thing, or it will return a null pointer. And the case where it would return a null pointer is if all the shared, right, is a ref-counted pointer, if all the strong references to that object have been destructed, it went away, that will null out all the weak pointers. Okay? So what I need to do is acquire a lock to get a strong pointer to this object, and then I can do an operation on it. Right? So that's what allows cancellation. That's the complete implementation of my task cancellation. Right? And that's really all I need if I get fairly fine granularity tasks. Nobody cares about this thing anymore, don't execute it. Right? That's it. Okay. So now, our shared here, we need to implement the call operator that we just, that part right there that we were just forwarding to from the call operator on our package task. And so all we're going to do is we're going to execute our function that we're holding, and we're going to set the result in the parent half of our class with that. And then we're going to go ahead and clear out that function that we're holding to free up any resources that it's hanging on to. Okay, now we're done with it. Okay. So here's our base. We need our set function here. Okay. So here's what we're going to do. When we set, we need to store our value in our optional, the underscore R there, and we need to execute any conditionals that have been waiting for it. Okay. So we don't want to be executing those conditionals while we're hanging on to our lock. So we're going to create an empty vector to hold those continuations. Okay? And then we're going to lock our mutex. We're going to push the result that was passed in here. This is the result from executing our function. And then we're going to swap all of our continuations with that empty function. And that's all we're going to do while we're holding on to that lock. So we'll keep it fairly minimal. Oops. And then we need to notify anybody who's waiting on a get. Right? If you get rid of your gets, get rid of that line. And then we go and we execute asynchronously. Right? This is async underscore. That's the async we just built with our task system. Now we go execute all those continuations. Okay. So that's that piece. So now the future side of it here, right? So that's the complete implementation of our package task side. The future side here, we're going to hang on to a shared base pointer, so we need to fill out our constructor. Here's what we're going to do with our then. Okay, so this is registering a new function as a continuation. Okay, what we need to do is package that up, so we're returning a future for it. Okay, and we're going to wrap it in a little lambda expression there, and the purpose of that is to hold on to that shared pointer, okay, for the argument that it's dependent upon, so the system doesn't unravel. So we need some strong reference going back, right, so that we're building this chain up. Okay, so that's hanging on to that future. That's part of our chain. So that's the line p equals underscore p there. And then our get, we'll just forward to a get function in our shared data. Okay. So now our then clause is pretty simple. This is now looking down at the implementation inside the shared part. Okay. So we've got a bool flag that says whether or not we've already resolved this thing, which will determine whether or not our optional is empty. Okay, we're going to acquire the lock. We're going to check and see if we're empty. If we are empty, which means we haven't finished executing whatever is feeding into this future, then we're going to go ahead and push our continuation clause into our continuation list. Okay? Otherwise, we're just going to set this flag that says, no, we've already been resolved. And then if we've already been resolved, we'll just go immediately and take whatever continuation was passed here and say, oh, great, just go do that asynchronously with the result. Okay? And then our get function here acquires a lock, okay? And this is just spinning on our condition variable until the result is ready. So it's pretty straightforward. So that lets us build this structure. That's what the whole thing looks like. Okay. Now we can wrap the whole thing up by writing a little async function that has the same signature as C++ 11 async. So I can pass in a function, a bunch of arguments, bind those arguments into the function, package it up, throw it into our async system, and return the future. Okay. So now we have a complete kind of end-to-end tasking system that we built here. Now we're missing a bunch of features, right? We don't have exception propagation, we don't have broken promises, but this is so you understand kind of how all the pieces work here. Okay. And if you look inside C++ 11 futures, they have very similar structures, right? So now we can take the same code that we had before, and we can execute it, and that would actually be our result. Okay. If you notice, I'm not taking Fibonacci of 1,000,000 anymore, it's Fibonacci of 100. So it's pretty straightforward. So here's a big issue, and this is where we kind of turn the page. We've been talking about concurrency and futures and building the system up. Since this is a keynote, I wanted to leave you guys with something to start to discuss for the rest of the conference, right? And plant some seeds, plant some ideas. Building up futures, whether or not they're the futures that we just built, okay, or whether or not you're using C++ 11 futures or Boost futures, these are relatively heavyweight, complex, data structures that require a bunch of synchronization. Now, you can greatly improve the implementation of this with lock-free, but you won't get completely weight-free data structures. You can improve how you're using mutexes. You can optimize the crap out of it. You're still doing heap allocations, right? You're still doing something fairly complex. And what you're doing when you're executing your code is you're building up this long chain of dependency tasks, okay, to execute it exactly one time, right? You call the functions, and it goes through and it executes, and it gives you one result, and then your application will typically loop back around and build the whole thing again. Okay? So, what if you didn't do that? What if you built the data structure and kept the data structure and kept feeding values in on this end and flowing through? Right? If you did that, you would have just reinvented functional reactive programming. Okay? That's what you're doing. Okay? That's the model of a spreadsheet. That's when you hear data flow systems. That's what people are talking about. Let's build this graph and hang on to it, and now we can keep feeding values into it. Now, most of these systems still look very imperative in their form. Right? You're constructing this dependency graph, but you're doing it as if you were calling the functions and getting the tokens back, and in the background, it's building up this whole big graph. Okay? If you go this route and you start doing functional reactive programming, what you'll find is your graph actually changes over time. And it changes a lot, and you need facilities for how to change it. And if you look at an application in its entirety, you can think of, well, within that application, there is a fixed in some form set of dependencies in there. And then there's just multiple flows through those sets of dependencies. Okay? And so can you start to back up a level and say, instead of building this thing as if I were doing an imperative, even if I'm not tearing it down and I'm keeping it, modifying it over time, step back a little ways and say, how do these things all interconnect, right? And what does this graph really mean? And one way to do that is to say, maybe this function, this circular function, isn't just a function, right? What it really is it's that operation is representing a relationship between values. Okay? So if I have my function calculate the millionth Fibonacci, right? What I've got is 1 million is related to the result of calculating Fibonacci. Now, some of those operations can be inverted, and you can come along and say, given this number, which Fibonacci number is that? Okay? Not every operation. Fibonacci is a good example of one that's actually fairly difficult to reverse. But if you look at your application, what you'll find is that the way that this graph is changing is mostly in two fundamental ways. Okay? One is that these things execute relationships, and what we're doing is we're building the graph that represents the different directional flows through those relationships. Okay. And the other thing that we're doing is some of those relationships are conditional. They only apply at different times, so they get turned on and off in our graph. Okay. So that's the way our graph is kind of mutating over time. Okay. So maybe what we'd like to have is a system where we can step back a little bit and talk about those relationships. Okay? We can remove the arrows from our graph and just connect these things. And if we had a relationship that represented multiplication, we could provide 3 operations to satisfy that relationship of multiplication. Okay? This forms a particular kind of constraint system that I call property models. And I've been working on property models now for, I think, over a decade, which is pretty scary. I have a collaboration going with Texas A&M University. Look up, we have a number of papers published in this space. Okay. So how the flow is determined through these graphs basically depends on the events coming in, which is setting values, which raises the priority of those values, which determines how they flow through the constraint system and provide results. Okay. So how does this thing start to look? So we have this graph with a set of relationships, right? And initially it's undirected. We can flow through the system in multiple ways. But as we set values, those values become sources and they become anchored. Okay? And we flow through our graph. So maybe here I set my two sources, and this is the way I'm going to flow through the graph to satisfy those constraints. Now, reflowing a property model doesn't require all really. That's a bad phrase. So it doesn't require that I execute the procedures attached to those relationships. It doesn't require that I execute Fibonacci, okay, to resolve it. All I can flow the graph purely based on the structure of the graph and knowing the arity of the relationships and the directions that they can flow out. Okay? And so given that, I can flow my entire graph with a bunch of futures, say, and start to calculate my entire graph asynchronously. Okay? So what happens is this single graph becomes these multiple graphs that are changing over time. So I started with my two sources yielding my two results. And then the user comes along and they set another value. So now I have another source and that changes the flow of my graph. But that graph now, okay, so now I'm going to end up with the two sinks down here. This graph depends on the value from the previous graph point in time. Okay? And one of the old sinks there that's grayed out in the top right corner, I no longer care about. At this point in time, I've forgotten about him. Right? So that becomes a canceled operation, that circle there, and it drops out of my calculation. Okay. So a thought. We've been going through with C++ 11 and C++ 14 and C++ 17. And we're building these task systems. And we're tying together these sets of features, and we're patting ourselves on the back for what great innovation this stuff is. But really what we're doing is we're expressing the connections, the relationships between elements within our code, and we're doing it by writing a bunch of code that looks imperative. Okay? And instead, maybe we need to take a step back, okay, and start to think about what a system would look like if we wrote the graph, okay, if we wrote it directly. Okay? And there's a lot of information that's stored in that dependency graph. Right? I shouldn't have to be flowing futures around. I should be constructing my dependency graph and letting my compiler realize what can be executed in parallel, okay, and what has a big enough grain size to actually be worthwhile to put up with the overhead of scheduling it in parallel, and creating those tasks itself. So I'm hoping that plants a little seed. And if you guys want to see demos of what something like this might look like, I can show demos. But for me, it's thinking maybe we're going about programming these concurrent systems kind of from the outset in the wrong way. Right? We're coming at them, treating them as if we could pretend that they were imperative systems. Okay? And even though that makes it easier for us to make the transition, maybe that's not where we want to end up. And maybe as a bunch of computer scientists in this room, maybe we should start to think about where it is that we do want to end up. End of my talk. If there was a language barrier and I lost people, feel free to come and ask me questions. If people have questions here that they would like to ask, feel free. This is a difficult talk because it's way heavier in code than what I usually like to show. But part of the reason why I want to show it is because I think it very much conveys how complex this stuff gets under the hood. And a lot of times we look at something like an STD future and we don't understand the cost of that, right? So the cost of that is relatively high. And so if you actually crack it open and look at the code and understand what that cost is, I think you can better utilize them. So hopefully people hung on. Do people have questions? Nobody? Did I lose everybody?
Here.
Here.
I have a question about some controversy when talking about blocking features in structure. I know that Microsoft implementation doesn't block asynchronously run feature in the structure, while GCC and Clang blocks in the structure. Will there solid opinion between different vendors of the compiler regarding the blocking of the feature in the structure?
Okay, so the question here is there's a bit of a controversy going on because in the standard library there's std async, which returns an std future, and only in the case of calling std async you can create futures in other ways using promises. But if you call it through async and you get a future back, what the standard says and what GCC and what Clang do is when that future destructs, it blocks until the future is satisfied. Okay, it just waits until it's done and then it throws away the result. Microsoft did not do that. Okay, if you let the future destruct, your future is just gone. It destructs immediately. Microsoft, of course, has the answer correct here. We don't wait. We don't ever want to wait, right? Right. Destructing a future should actually cancel the operation, which Microsoft doesn't do, although PPL does provide some cancellation facilities. They're very hard to wire up for that particular case. But we don't want to wait. More importantly, Microsoft on Windows 8 really can't implement it the way the standard states without a bunch of hackery. Because inside of Windows 8, they've pretty much hidden the access to threads directly. So when you construct a thread, you don't actually get a thread. What you get is a simulation of a thread sitting on top of the Windows thread pool. Okay? So if they start blocking tasks inside of their thread pool, what you're going to end up with is your machine grinding to a halt. Okay? Because you're not spinning up multiple threads every time you create these things. You're just, if you've got 8 cores, if you spin up 800 threads in C++, you'll be running a bunch of tasks on 8 threads inside of their tasking system. And so if you start blocking those, the machine just dies. So Microsoft really can't back away from that decision. I think a blocking feature is the most idiotic thing I've ever seen. It drives me nuts. So in this case, I think Microsoft is correct. I don't think they go far enough. And I'm hopeful. I don't have any strong insight. I don't sit on the C++ committee, but they ask me questions a lot. So I'm hopeful that this gets resolved in C++ 17 correctly. So that's my answer on that. Are there other? Check. Okay. Pass around the microphone here for the questions.
I have a question related to property graph. As I see in property graph, I can change the direction of my graph calculation, and it looks like it's okay for my scheme. But usually I have a function, for example, it has A as an input parameter and B as a return value, right? And I don't know easy way how to create an automatic translation this function to another function that accepts B and returns A. So how it connects to the, how I could use this in a real life?
Right, so the question there is when you start talking about graphs that you can reflow through these relationships, some of your functions might not be invertible or not easily invertible, and so how would you actually use this in real life? In reality, a lot of functions are not, right, which is why functional reactive programming is so popular. I think if you were constantly backflowing through things, it would be much more challenging. So I'm not saying that all of them are, right? It's just that when they are, it's nice to package them up in this form. There's lots of benefits and lots of things that you can prove about the system under those circumstances. So yeah, certainly not everything is invertible. Yeah.
As far as I understand, you construct your data graph in runtime, yes?
Currently I do with property models, which has kind of been an ongoing research effort. They don't necessarily have to be. I would love to see them constructed.
My question is, maybe it's better to construct this graph in compile time, and maybe it allows few additional compiler optimizations or whatever.
Yeah, I think absolutely. Constructing the graph in compile time is where you want to end up. There is much more that you can do with it. I've also written a set of tools. Once you have one of these reflowable graphs, you can do things like very quickly make sure that for any set of input values it is flowable, to never end up with an over-constrained system. It's actually a fairly simple algorithm that you can run through to prove a system correct. And it would be nice to just have that kind of built into the compiler and say, just do a quick static analysis and make sure that my model is correct and that it's always flowable. So, yes.
So I must confess I don't know much about functional reactive programming, but what came to my mind when you mentioned this property graph or the dependency graph is declarative programming, which also just describes the relationship between different results and lets this runtime system or the compiler figure out how the solution should be.
Yes, absolutely. This is moving things out of an imperative space into a declarative programming space. Property models have a lot of similarities to declarative constraint systems of various forms and to rule-based systems like Prolog. Property models, kind of as described here, are not a complete solution. There are other constructs, other forms that these graphs can take that are not describable easily inside of one of these graphs where you just remove the arrows. Things like a grammar is not easily described like this, but a grammar is described declaratively through like an EDF, through other mechanisms. So I'm not making the claim that all programming should look like property models. In my opinion, it actually hits a nice sweet spot in that it's an extension to functional reactive programming, and so it lets you solve some problems that you can't solve in functional reactive programming easily. Lets you get a little further. It also makes the graph explicit as a data structure, which means that there's a lot of ways to do reasoning about the graph. Most functional reactive programming doesn't do that. It builds the graph up at runtime, but there's no way, kind of like in the futures dependency, there's no mechanism to say, let me traverse the graph, right? Tell me how many nodes are in the graph, what's the topology of the graph. And there's a lot of interesting analysis that you can do. You can do things like, if you think about building a UI, if you see a widget within your UI, like a text edit field, go dim. Okay? The reason why a text edit field dims within a UI is one of two reasons. Either that value is implied which means that I have a hard arrow going into that value, and so I can't change it, right? There's no way to backflow that result in the current state of my graph, okay? Or, in which case the text edit field should be dimmed and it should show the value that it's currently set to. Or that item can be a disconnected component, right? I can run a connected component algorithm on my graph, and I can say currently there is no path from this value to the results that I care about. And so therefore this item should be dimmed and it should just show whatever last value it had. Okay? So those are the two reasons why within a UI an element might be disabled, might dim out. And yet, how many times do people using UI toolkits write, oh, when this thing happens, dim this UI element? And how many times do you see bugs in UIs where something is dimmed when it's not supposed to be dimmed, or enabled when it's not supposed to be enabled, or dimmed and not showing the correct value? Okay? All of that information is in how those values that you're seeing in the UI are interconnected and related. And you can extract, is this thing dimmed or not, by simply analyzing the graph. So, hopefully that helps answer it. Somebody back here. Oh, go ahead.
Sorry. Do you know something about the future of step future? Will it be duplicated? Will it be removed? Will we get additional implementation?
Yeah, so from what I've been following, I haven't read all the papers on where C++ 17 is going. I've been following a lot of the conversations. It looks like we will get a win-all mechanism. So we will have joins. We'll have thens, so we'll have continuations. I really doubt that cancellation is going to make it. A lot of people, when you talk about canceling a task, immediately people think about canceling the thread, which is a very different thing, right? Taking a thread that's in the middle of processing and just killing it leaves your machine in an undefined state and is a really bad thing typically to do, right? There's very few circumstances where you would ever want to just kill a thread. When I talk about cancellation, it's like it's not that. It's just don't execute this thing when nobody cares, right? Right? And it's because the semantics and the language get confused. It just quickly becomes this very controversial thing. And should you provide a way to cancel a task that's already started to execute? My opinion is maybe, but most of the time the right answer is to carve that big task up into a bunch of small tasks. And for me, if I'm going to scale down to one core, no thread support, no parallelism, then I have to do that anyways. So, to keep the UI interactive, right? If my tasks aren't very, very fine-grained, my UI just freezes. Mike? Oh, sorry.
Hi.
Yeah, he's picking people.
Can you open the slide where you show what part of the machine I use with GPU, SSC, and multi-threading? So my machine has 32 hardware threads, and vector units can fit only 2 doubles. So it looks incorrect to me.
It'll be a little off. This is an 8-core, 3.5 gigahertz Sandy Bridge with an AMD. So yeah, the scale on that changes a bit depending on what desktop machine you're looking at. If you're looking at a device like this, then you get maybe up into the 10% range for one core, of the processing, right? So that's the graph for this machine. But yeah, I mean, slide those around a little bit.
I would say quite dramatically.
Yeah. I think it still makes the point that if you're only lighting up one thread, you're not using your SIMD unit, and you're writing in plain C++, you are way underutilizing the machine. Where way is somewhere between you're using 10% of the machine and effectively none of it.
Thank you. I have another question. what are the most common types of bugs that you see when you program in this style?
What are the most common bugs that I see? So the first thing that I see is, well, are bugs caused by others circumventing the system, I think is the biggest problem. Is people come along and they say, well, I will register a task that doesn't return a future because I finally need to get my output. I need to step out of functional programming and stop just generating heat and do some I/O. And in C++, we don't have monads, a formal mechanism for that, so people do the equivalent with a whole bunch of mutexes, and it gets bad. The way you actually want to do it, there's two ways. If you think, oh, I build this chain of futures and I do .then, and Sean says I can't ever use a get, right? Now I get to the end of my .then, and I need to go modify this shared object. I need to put the data back in my document, or something like that. There's two fairly common ways that you can do that. One is you can treat the last future in the chain, holding onto it in your document, as if it were kind of a single element communication queue. And so you can have a pulling model where every time I would need that value inside of my object, I would say, is the future ready? If so, get it out and start using it. Otherwise, just ignore it, right? So I can use the ready instance on a future to control that. The other thing that I can do is you want each object conceptually to be owned by a single thread. And when you're dealing on desktop systems and iPads and stuff, you tend to have a lot of limitations where things have to be done on the main thread. But you can queue that last operation to a serialized thread that's serialized, like probably your main thread, but you could create other serialized threads that serializes the access to the object you finally want to set the value in. So your last future says, oh, stick this into a serialized queue, and then in a run loop or some mechanism that's controlling those objects, this thing will get pulled out and executed. Right? It's like sending a message on Mac OS or things like that. And that's where most people get hung up, is they don't know how to get that last piece of data back, so they throw in a bunch of mutexes and everything falls apart. That's the biggest problem. The other problems that come in are you get stuck, right? You build up the system and you say, I really just needed this little bit of information from that thing over there, and I don't want to go reconstruct and rework and re-architect my system. So maybe I could just set an atomic or throw in one mutex or whatever. And I see lots of bugs caused by people trying to do that. So those are the two main issues. Other than that, it takes a little while for people to wrap their head around it. If anybody's done much Windows 8 programming, anybody there done Windows 8 programming? Yeah, Windows 8, the API is very asynchronous and lots of features, and it takes a little while to wrap your head around. I call this function, and it's going off and doing something in the background, and you end up introducing race conditions because you're not thinking about it. You're just accessing things directly. So I see people do that. And you just have to say, look, these functions have to be pure, right? Which is why value semantics are so important, because you want to be able to kind of package everything up, give it ownership to your task that you feed off, and make it as a pure function. If you're accessing some object that's outside of that, if it's not a pure function, if it has side effects, all of those side effects have to be synchronized. Don't do it. Other questions?
You were talking about fine-grained tasks, right?
Yeah.
Just divide your bigger tasks into small tasks. But you also mentioned progress reporting among the feature you are missing, and task cancellation. So I believe you need progress reporting. It applies only to bigger tasks. And when you have bigger tasks with progress reporting, maybe you need to cancel already running tasks.
So it doesn't. In the same way that. Do people need me to repeat the question? You said I talked about one of the things that I want is to understand the progress of where a task is. And that seems running counter to splitting up tasks into a bunch of fine-grained tasks. Well, what you have to do is if I create a task and it spawns out a bunch of tasks, then those are all part of the whole. In the same way that I'm building my dependency graph for cancellation, so that if I let go of the last future, the whole system unravels, I use a similar mechanism for tracking progress. And the way to do it is to say, okay, the first top-level thing, we'll assign it a value of 1.0, and as it progresses, it will just set a double and say, how far am I between 0 and 1.0? And when that operation feeds out subtasks to go do, it will say, you are the subtasks, your 0 to 1 is my 0 to 0.2, okay? And initially when you write this, you don't even have to fill in those values. What you can do is say, we'll just mark them, we'll divide up evenly. If I have 100 subtasks, we'll just say divide by 100, and that will work pretty well. And the first time the system executes, you remember all of those values. And so the system can just be self-adjusting. So you can put up a very nice progress bar and watch it go kind of smoothly across. It's actually a technique that Photoshop uses. If you ever see a progress bar in Photoshop, it's doing a ton of stuff, fanned out on all your cores, and it's tracking them that way.
Well, it's sometimes desirable to pack some updates together. If for example, we have multiple callbacks from some features to update the user interface, and we, if they happen to be simultaneously, we want to make sure that this is only one. There will be only one callback called. Is it possible to make this somehow automatically with features?
So the question is, sometimes you want, in the middle of some task, to be updating your UI, but logically you're kind of only thinking about this thing as being one feature. How do you want to do that? That gets you very much into the space of functional reactive programming, which is really what I want is a stream of values getting fed into my UI that's updating over time. So I'm constructing this graph and I'm feeding things through it, and it's got a constant stream of values feeding it into my UI, right? So you don't want a single future result for that. In functional reactive programming, it's usually called a behavior, which you can think of as a future that keeps executing the continuation multiple times, right? Every time it's got a new value to update. So that's how you solve those problems.
Hello. My question would be about the costs of breaking a larger task into smaller pieces.
Yes.
This is obviously required for the scalability, for better scalability, but increasing the number of states, but it blows the number of states the system can be in, right? More or less.
Yeah, more or less. So if you look, one of the features that hopefully will make it into C++ 17 comes out of Microsoft's work, which is await and yield. Do people know what that is? Anybody? A couple people. So the basic idea is I've got a loop, right? That I'm spinning over to calculate something. Maybe I'm processing an image, and it's kind of a pain if I have to take that loop, which is one task, and it's too big, and how do I bust that loop apart so that I can execute it as multiple tasks, right? Sometimes it's fairly easy, but sometimes you have a lot of state inside of that loop for what you're doing. So the idea with await and yield is that I can have what looks like a loop, and in the middle of it, it can be yielding results back out, and I can have something else that's potentially awaiting on that, and it basically lets me take my single loop, and I write it in my code as a single loop, but it executes as if it were multiple tasks. Okay? So that's how that works. And the way that it works is it packages up what the loop is accessing into a function object, and it just keeps rescheduling it onto a task queue.
Thank you, but that's just a technique, right?
What's that?
That's a technique.
It becomes
a mean to how can you do it? How can you achieve this breaking up, right? But
yeah.
Does it have some performance costs?
It does have some performance costs, certainly.
Do you have some results like how does broken task behaves compared to the same task if you had written it for the single thread in the first place?
It all. I mean, this is where you really start to want. So the question is, do you have some results about what the performance impact is of? Oh, for that stuff, yeah, we do. But for image processing, when we break things down, it's very much a data parallelism problem, which is slightly different than what you typically do with a tasking system. We're still executing them on tasks in the thread pool, unless we're doing it on a GPU. But they happen to divide very easily, right? The work for image processing tends to divide fairly easily. So we're able to scale pretty well. Overhead does eventually kill you. It does in many of these systems. We can also adjust the grain size to trade off both interactivity and performance. So I think the grain size in Photoshop right now in the desktop is like a megabyte size. In Lightroom, it's much smaller because it's a very different architecture, trying to stay within L1 cache. Yeah, I mean, I can point you to papers. There's been a ton of research on what the cost is of splitting things up into multiple tasks and how you calculate grain size. And years ago, I worked with Arch Robinson, who wrote Intel TBB, which originally drove me nuts because for Intel TBB, for their data parallelism stuff, you had to specify grain size, which is basically how much do you divide your task, how big of a piece of work. So you had to tell the system, oh, for this job, I want a grain size of 27, and these were really meaningless numbers. And if you actually look at the performance graphs, it's not. There's a sweet spot, right? If you have a grain size that's too small, your performance sucks, and if you have a grain size that's too big, your performance sucks. And so it's a saddle graph, right? So you want to find the minimal point in that saddle. And I went round and round with Arch. I'm like, look, you can put this in here, but I have to tune that number very carefully for a single system and one execution environment. And if I want to run across a variety of machines, I have to build a big whole table. And it takes a lot of effort to manually find the low point in that saddle, right? When you start out, you don't know where you are in the saddle, so you have to write these isolation tests and plot the curve and find it. I said, nobody can do this. Nobody can use this system. So we went round and around and finally worked out an algorithm that does a fairly good job at guessing at where the low point in the saddle will be. And it's not optimal. And they still have in TBB an optional grain size arguments if you really want to tune the heck out of the thing. But that's kind of the best you can do right now, right? You know, if you look, the reason why we don't have computers outside of GPU, or it's a data parallelism problem, that have 65,000 cores, is because of Amdahl's law, because even if we have something that conceivably had that much parallelism in it, the overhead kills us before we get there, right? I mean, if I went to Intel tomorrow and said I figured it out, I could make Photoshop run on 65,000 cores, I guarantee you Intel could build it. But I can't. Nobody can. Okay. So that's why. Why did Apple go on this guy? They went with a 64-bit ARM chip with 2 cores instead of going the direction the rest of the industry was going, which is stay at 32-bit and put 4 cores. Apple kind of bucked the trend. The reason why they bucked the trend is because for most apps, you get better performance out of going with a wider register set than you do out of adding additional cores. Partially that's because most software sucks and doesn't scale. I could light up 4 cores, but they didn't ask me. But that's the trade-off, right? I mean, that's the world we live in.
Could you please recommend or mention some good and reliable functional reactive programming libraries that we could use? Because I think that for most of audiences this topic can be interested. Maybe you could recommend some with FRP library.
That's tough. I mean, probably the best thing out there. Yeah, I mean, because the question is, can I recommend a good functional reactive programming library for C++? Eventually, I'm going to end up building one here. No, unfortunately. You know, Microsoft has their RX library, which is probably the best library out there, but I don't believe it's open source. So it is open source. Okay, so Microsoft's RX library. For functional reactive programming would be my recommendation. I tend to do my stuff with unfortunately kind of a very messy mix of partial solutions that are built into various products. And that's something that I'm trying to remedy right now. We actually have 2 efforts inside of Adobe, one doing it from C++, which is my side, and somebody else doing it from Lua, which is quite popular. Okay, I think we're supposed to hit break, so everybody is.
Yeah, thank you, Sean.
Yep.
Да, я так понимаю, что у нас возникли проблемы вначале со звуком, потом с изображением. У меня большая просьба, если вам плохо видно, может быть, вы поднимете руку, встанете и скажете об этом, потому что не всегда мы успеваем. Мы сейчас попробуем это исправить, чтобы на остальных докладах было видно хорошо даже с задних рядов. Ну и, конечно, если вам не слышно, то тоже можно найти меня, или вы видели молодого человека, который с микрофоном, или подойти на стойку регистрации и сказать, что плохо слышно. То есть, фидбэк приветствуется. Я вам напоминаю, что сейчас будет кофе-брейк прямо под нами на 2-м этаже. Вот там такая дыра, прямо в этот ресторан. Если вам захочется пить, то есть можно прыгать, да, я имею в виду. Если вам захочется пить, еще секундочку, у нас прямо там в том углу стоят кулеры с водой, пожалуйста,